So we're going to start off this chapter by looking at a method for solving systems of linear equations called Gaussian elimination. That's one of the first things students usually learn in an introductory linear algebra class. So just from a very high level, our goal is going to be to take an n by n system of linear equations, convert that to the corresponding augmented matrix, use the three elementary row operations to get the matrix into the so-called row echelon form. Then finally use back substitution to get the final solution to the original system. Now there's one notational item I want to point out before we go any further. When we made the transition to the augmented matrix, I replaced the b variables with properly indexed a's. Right? At this point, there's really nothing special about that column anymore. It's just another set of values in the matrix. And our lives will be easier later on if they're referenced using the same indexing notation as all the other values. So I do want to take a minute just to review the notation I'm going to be using from linear algebra here to talk about those elementary row operations. First, I'm going to refer to each row in the augmented matrix by a capital R with a subscript indicating the number of the row. So this notation, where I have two rows and a double arrow between them, that just means flips the values in the rows, right? Just switch one with the other, not actually changing any of the numbers along the way. This is going to mean take every value in row I, multiply it by the constant a, and replace it with that value. Okay, so we're updating a row in place with this. This is very similar, but it takes two rows. I'm going to take row I and row j, add their values together column-wise, and put that new value back into row I. And finally, this isn't really an elementary row operation. This combines two of them, but I wanted to mention it specifically since it's something that's going to come up repeatedly in our discussion of this algorithm. This takes every element in row j, multiplies it by multiplies it by a, adds it to the corresponding value in row I, and replaces the value in row I with that new number. Okay, so with that notation in mind, let's talk a little bit about the algorithm itself. So our goal is going to be, as the first step, to convert every value in the first column below the first position into a 0. So to eliminate the value in the A21 position, we'll use this operation acting on the second row. Now, if you think about what this does, specifically to the value in the A21 position, the left-hand side simplifies to 0, which gets put back into the A21 position, which is exactly what we needed to happen. Then the process repeats with the third row with a new multiplier, right, chosen so that the A31 value becomes 0, etc. Now, of course, every value in each row is getting updated by the row operations, but it's just the value below the main diagonal that we need to have a specific result, right? Then we choose the multiplier to make that happen. So our end result, once we've been through every row, is a new matrix with zeros in every entry under the main diagonal. Now notice the notation that I've used here. The superscript 1 indicates this is the matrix generated by the first pass through the algorithm, the one that cleared out the first column. Now it can be a little clunky putting the superscripts on every entry in the matrix like this, so in general I'm going to omit them with the understanding that these A's are different from the A's in the original matrix, right? So I'm only going to use the subscripts in the case where we're talking about two different matrices and we really need to be clear about which one the values are coming from. So to put this in more programmatic terms that'll lead us toward our final algorithm, to update a given column, we're going to loop through the rows below the main diagonal in that column, the current column that's being processed, updating every value. So to get to the final elimination algorithm, we're going to have to add another loop that goes through all the columns. Right? Now notice that there's no need to process column n. Right? A sub n is the last value on the main diagonal, and the values on the main diagonal don't get eliminated. So the inner loop now is going to start at j plus 1, which is the first row below the main diagonal in the column that we're processing. And we're going to eliminate from there all the way down to the bottom row. Now, there is one additional concern we need to check for. So take a look at this example here. If we execute this operation on each row, right, in column 1, then we're going to get this result. But there's a problem here. The next value on the main diagonal is equal to 0. And that's an issue, right, because that's the value that goes in the denominator of the multiplier. Now, fortunately, this isn't a complete deal breaker. In this case, we can execute a switch operation between rows 2 and 3. That's going to move the non-zero pivot in row 3 up to row 2. Now the algorithm can proceed just like it normally would. All right, so this is just going to add an additional check to our algorithm, right, where we check that the current pivot isn't 0. And if it is, then we find the first non-zero value below it and switch that row with the current one. Now, in the case where there is no such value, that is where every number below the main diagonal in that column is 0, then the algorithm stops. We return a message saying that the system is indeterminate and we can't go any further. So this brings us to the backward substitution part of the algorithm, which is going to actually give us our final solution. So to see what's happening here, I think it helps to convert the matrix back to the original system of equations version. So to get the final results, we'll start with the last equation, which we can solve just by dividing both sides by a sub nn. Now, from there, we'll move up to the second equation from the bottom, which we can solve for x sub n minus 1. And continuing this gives us this result for x sub I. Now, obviously, that's a little messy. Right? We can state this more concisely using the sigma notation, and this will also help us see where we're going to do our loop in the final code. Okay, so with those tools in hand, we can state the final algorithm. All right, so first, I want to explicitly state what we're trying to do here. So our goal is to solve the n by n linear system of equations given by this set of equations here. Our input is going to be the number of unknowns or equations n, and some languages don't need that. Python, for example, can figure out the size of a matrix all on its own and be just fine. Other languages, C, for example, it's going to need to be told in advance how big the matrix is. And finally, an augmented matrix, A sub ij, where the i's, those are the rows, remember, go from 1 to n, and the j's go from 1 to n plus 1 because the columns have to also have that column with the constant values. And finally, our solution is going to be a set of numbers, x sub 1 through x sub n, or a message that the system has no solution. Okay, so I'm actually going to do this in 2 parts just because of space considerations here. This is the elimination part of the algorithm, and it's going to start by looping through the columns. Now, I know it's more standard to use I on the outer loop and J on the inner, and I've got them flipped here. And I've done that since in linear algebra, it's customary to use I for the row index and J for the column index. And the outer loop is looping through the columns, which is why I put J up there instead of the usual I. Now, the next block does the check to make sure the current pivot value isn't 0. It moves a non-zero value in if it is and returns, I don't say an error, there's nothing wrong. It's just that there is no solution in the case where there are all zeros below that entry on the main diagonal. The third section moves through all the rows below the main diagonal in the current column, eliminating the values in that current column. And finally, of course, there's the last check here to make sure that that a sub n value, the last value on the main diagonal, didn't get eliminated at the last minute. Again, that would make the solution indeterminate. So At the end of that part of the algorithm, the matrix is in the row echelon form, and we can work through the backward substitution part to get the final solutions. So this starts by calculating the value of x sub n, then it loops backwards through the remaining equations, calculating each result using the formula we developed on the last slide, and of course finally it returns the final result. So from a memory utilization perspective, we can do the entire algorithm in place just by replacing a sub ij with the newly calculated value at each step. And since the values below the main diagonal that are set equal to 0 are never touched again, we can also kind of go a step further and store the multiplier values there. Doing that is going to be useful in some of the other algorithms that we'll be discussing later on. Okay, so this means that in the end, each matrix A superscript k has the newly calculated values above the main diagonal and the multiplier for each row below the main diagonal. Okay, so before moving on, I'd encourage everyone to try to implement the algorithm in your language of choice. That's really the best way to understand exactly what each step is trying to accomplish. So in the next lecture, we're going to use our algorithm to determine the efficiency of the method by determining its asymptotic runtime.